Let's look at functional groups' effects on acidity. And so in a previous video, I talked about how carboxylic acids in particular have similar acidities to each other. So if I draw up benzoic acid and I compare that to acetic acid, these have very similar pKa's. Benzoic acids is about 4.2 and acetic acids is about 4.75. And so these are kind of similar. However, if we start doing some things nearby, like changing the functional groups, we can get the acidity to change. So let's look at what would happen if we put an electron withdrawing group on acetic acid, or rather 3 of them. And now we have trichloroacetic acid. And the chlorines have a significant electronegativity, and that will increase the acidity. So somewhere around 0.77 pKa. That is a lot more acidic. And in fact, this acid can have a much greater effect on your skin than these others. Sometimes this is used in chemical peels or various treatments that you might get at a dermatologist's office. Let's examine the effect of this chlorine in another context. So we'll look at butanoic acid. So to do a proper comparison of this, we'll start off with just butanoic acid with no halogens on it. And it has a very similar acidity to these other carboxylic acids. However, if we start to put a chlorine on the molecule, then we can see an increase in the acidity. So let's try putting a chlorine way out here on the 4th carbon. Well, we've increased the acidity a little bit to 4.52 pKa. Let's move the chlorine a little closer. We'll put it on the 3rd carbon now. In this case, we've increased the acidity a little bit more, again, to 4.05. Now let's put it as close as we can on the 2nd carbon. And now it's only 1, so it won't ever really get to this level because this has even more chlorines on it, but this will be the most acidic because the proximity of the chlorine has gotten a lot closer to the carboxylic acid group. Let's look at another system, just the phenol system. And I wanted to go over why phenol is acidic in the first place. And then we can talk about some functional groups on there. So phenol just by itself has a pKa of about 10. And if we deprotonate it, we can see some of the effects through the resonance stabilization. So we can start off with a negative charge there, but we can move the negative charge around the ring a little bit. Now the negative charge is on one of the carbons in the ring. And we can keep moving this around a little bit. Actually, no, the arrow's going in the wrong direction. That should go there. And so you can see there's 4 resonance structures for phenol. And so therefore it's resonance stabilized. Now let's talk about what we could do to change this a little bit with some functional groups. If we were to put electron withdrawing groups at any of these resonance stabilized negative charge locations, that would increase the acidity of the ring a bit more than otherwise noted. And let's look at one of those examples here. So let's imagine that we have a carboxylic acid and a phenol. Now this is a little bit complicating because both of those groups are acidic. But the carboxylic acid is more acidic than the phenol. But a carboxylic acid is also electron withdrawing. This likes to pull electrons away from the ring. And so if we were to somehow place that at one of the positions where the negative charge would like to be, that could increase the acidity of that phenol. And so now I'm just going to draw up all the possible dye substitutes. So we have 1 carboxylic acid. And I'll just put it up at the top here. And we have a phenol in the ortho position. And we could draw it where the phenol is in the meta position. And then, of course, the para position. Now, based on what I just told you, we should think that ortho, right, there's 2 negative charges, should be an acidic position, and para should be an acidic position. And we do see that the ortho or the para phenol is a little bit more acidic than the metaphenol. This one is about 9.9, and it's a little bit more than just regular phenol because there is some electron withdrawing on the ring, and that does help stabilize some. And similarly, let's see here, 4.8 for the carboxylic acid, and this one is 4.58. And this one, since it's in the para position, is 9.4. So because this would put a negative charge right here next to this electron withdrawing group, it's a little bit more acidic. Now, you may have noticed that I didn't do this one yet. That's because it's different. So this carboxylic acid is a lot more acidic than these. This one is 2.97, and this phenol is a lot less acidic than these phenol hydrogens, 13.6. And so we don't just look at the electron withdrawing ability for the other groups. We have to consider a few other things. And so I'm going to draw this with this first proton removed because the carboxylic acid proton will come off first because it has a lower pKa. So let's look at what could happen on that structure. So I've deprotonated this carboxylic acid. And I'm going to draw my hydrogen explicitly in. And now you may notice something. This hydrogen is in position to interact with the carboxylic acid oxygen, the deprotonated one right here. And it can do some hydrogen bonding right there. Or realistically, it's going to be shared. This hydrogen is going to be shared between this carboxylic acid and that oxygen right here. That stabilizes this structure. That's why the carboxylic acid is a lower pKa. That's also why this phenol hydrogen is a higher pKa, because now you'll have to steal this hydrogen away from two oxygens. They're both kind of interacting with that hydrogen right there. And so since it's helping to stabilize that negative charge, it's going to be harder to remove that hydrogen. So let's review. When we have electronegative elements or atoms attached to our molecules that are acids, we can increase their acidity. And this holds true for more than just carboxylic acids or phenols. This holds true for any molecule where you could have some acid-base functionality. The closer we move the electronegative atom to the acidic hydrogen, or the most acidic hydrogens, the more acidic it will be because it has a greater stabilizing effect on the resulting anion. If we have more electronegative groups, that will have a greater effect than just one. Resonance plays a role in the stability of the anions. However, we do have to keep in mind that proximity to hydrogen bonding groups can have a big effect. on what we see on the acidity. So, thank you for joining me for this video, and we'll see you in the next one.